Hi, I'm Anisha Gautam, and I would like to present my research on condensation in biotech and API facilities. Biotech and API facilities with sterile areas are constantly working towards methods to mitigate the problem pertaining to moisture and temperature control. Within the building exterior wall, there will be a point where air diffuses from building's warm interior to cool exterior and reaching its dew point within the construction of the building itself, turning water vapors into droplets. This is called interstitial condensation. This is a very concerning issue for cold and sterile facilities as many problems can be caused by these water droplets, like mold growth, staining, corrosion, poor performance of insulation, damage to the equipment, electrical failure, bacterial growth, and so on and so forth. Over the time, the problem can worsen and affect the integrity of the building material and even the structures. But there are ways to measure this risk and mitigate it at early stages of design. A global integrated design project that I led from Indian division, me and my project lead from Ireland, we saw similar problems and found a solution using building performance simulation. The project was a biopharma facility in northeastern Ireland. The construction of the building envelope in building expansion was to be constructed using the prefabricated modular interior panels and modular structural system, in addition to be covered using a rain screen facade on the exterior. The rain screen facade system comprises of metal studs, a level of external sheathing, vapor barrier, followed by an insulation and metal panels. The airspace between two modular interior construction and the exterior rain screen facade was a place of concern that might pose a risk of condensation. As we have formerly received a basic training on few computational software to mitigate condensation risk in projects, I decided to do a study, and I basically wanted to see the space between these two kinds of construction and if they would pose a threat of condensation. The project included an existing Class C facility and an additional wing to be planned on the south facade. The new construction marked by dotted red line was primarily to increase Class C spaces including cold storage, control room, mechanical rooms, buffer platforms, etc. To test this building envelope, I used a software called WUFI. It is a German software to calculate 1 and 2 dimensional heat and moisture transport in walls and other multi-layer building components exposed to natural weather. We have one license in Jacobs and anyone can remote access into the system. So first, I understood the conditions of design. We can customize the design conditions as per the project using the inputs like material assembly, which basically includes construction and material parameters, the orientation and inclination of building, and both inputs are to be put by architectural department. The second is the surface transfer coefficient, which comprises of surface transfer properties for exterior and interior surface. You can specify the heat transfer coatings, radiation absorption, the emission, etc. You can also specify the heat transfer and the possible coatings that you want to apply to the facade. So basically these are the default settings of the material. These are already preloaded into the software and you can customize this if you have material information from the catalog. Then there are calculation period. So basically this is duration of the simulation, of how long you want to run the simulation and for how many days or years. Next is the location of the projects, so which is depicted from the outdoor climate. So I pulled it out from Energy Plus, a free open use software. And lastly, we have inputs from HVAC and process that we need for indoor climatic conditions. These can be defined as per standards of location of the projects. So if you're using the ASHRAE or the European standards, that can be defined. And these basically include the temperature and humidity air change rates. HVAC requirements of the room needs to be confirmed by HVAC department. This is like one collaboration work with inputs from every department. For assembly, there are databases available for different countries and regions, general building materials, especially materials that can be created for specific projects, One can also figure out the R values of the wall section using this tab. Then the second is the monitor position. This is very crucial because monitor position is the location at which we want to measure the external assembly temperature. At the beginning of the project, I tested multiple monitoring positions for each wall section to find out the weak points in the assembly. And lastly is the temperature versus dew point graph, which portrays the temperature at monitoring position that was selected in the previous section. It has time on x-axis and temperature on y. It gives a clear picture of when the test assembly will fail and have condensation. The moment the temperature to this wall section, which is red, meets the dew point of the assembly, which is purple, is where the problem lies. These graphs depict at what point in one system does this potential hazard occur, based on the data inputs that includes weather conditions from regional data material, conductivity, interior environment information, and etc. Ideally, the temperature should be more than the dew point at all points to prevent condensation. I first identified and listed out the scenarios that could pose a risk of condensation. So I have listed a few cases here that I wish to discuss. I tested out almost 20 to 30 different sections throughout the exterior facade, so I have an informed decision. So basically, the first is the assembly, which is including the rain screen facade and the modular construction system at the cold room of the south wall. The monitor position of this graph lies within the airspace as marked on the picture. And in this graph, we see clear issue with the proximity of the temperature versus the dew point in the airspace. We'll have condensation over time, therefore degrading the building materials around it. While testing in other sections, we saw that condensation was happening only outside of the cold room wall. The wall section in the mechanical space, which was on top of the cold room, had no possibility of condensation, and the section of the control storage also showed no risk of condensation. So basically, the exterior rain screen facade that we had designed was mitigating the problem of condensation, but the low temperature of cold room was causing the issue. So the idea came about, what if we ventilated the cavity with temperature same as the mechanical space above? The airspace will never become cold enough for it to reach the new dew point temperature. Then, the ventilated cavity solution was also tested out in all different joint conditions around the cold room to make sure that this was effective. So now you can clearly see that the red line and the purple line do not meet. So that means the temperature and the dew point line are far apart. So they will never meet and there will never be a condensation in the building. So I tested sections for both cases of interiors and the exteriors so I could make sure and have informed decisions on whether the building section was apt or not. Then the ventilated cavity solution was also tested in all different joint conditions around the cold room to make sure that this was effective. So now you can clearly see that the red line and the purple line do not meet. So the temperature and the dew point are far apart. That means they don't meet and there will never be condensation in the building. So I tested the section for both cases of exterior and interior to make an informed decision. And even if we needed to add more insulation to the building, the ventilated cavity and the cold room, they'll not have any condensation. This is a good way to analyze the result by creating video of the section over time. The advantage of this is that all points of the building section can be viewed at once and we can choose to monitor whichever position we need to study in detail. You can clearly see on how close the temperature and the dew point line is in the video. This is running through time and you can see how temperature of the construction is changing. So lastly, the conclusion. The wall systems were designed to prevent improper moisture intrusion. The study found a deficiency in the composite wall system at the first floor for 2 to 4 degree cold rooms. And the ventilating the air gap outside the cold room wall will need to be provided to mitigate the moisture problem. The existing facade was built with insulated metal panels. The client was also facing the problem of condensation in the existing facility, which was also causing damage to the equipment installed inside the facility. Therefore, we decided to conduct the same study and propose an ideal method of construction to mitigate the client's problem. This analysis was constantly checked and monitored by my senior project manager, Mr. Suhane Prakash at Jacobs, and HVAC engineers. Thank you.